Good evening. I'm Gernot Heiser, John Lyons Chair at UNSW Sydney, and it's an immense pleasure to welcome everyone to tonight's John Lyons Distinguished Lectures. We have an extraordinary speaker. I'll get to that later. First off, standard housekeeping, in case there's an evacuation back there and out to the left, which is where I guess almost all of you have come in, and toilets, they are right at the back there. So we'll have, after the welcome and opening, we'll have the talk by our distinguished speaker. And after that, we have a question and answer session. You're encouraged to submit your questions to the Slido. There will be a link up if you haven't seen it yet. I'm also happy to take questions from the audience live. We'll probably intermix them to minimize delays. And that's pretty much it. So I'll now introduce our head of school, Professor Akotsomya, for the actual opening.
So it's my honor and privilege to welcome you all to the event today. I would like to acknowledge the Bijigal and Gadigal people that are the traditional custodians of this land. I would also like to pay my respects to the elders, both past and present, and extend that respect to other Aboriginal and Torres Strait Islanders who are present here today. Welcome again to the 2025 John Lyons Oration and Distinguished Lecture. We will hear about our distinguished speaker in a minute. But before that, I'm going to say a couple of words about the school and my own personal memories of Professor John Lyons. So CSE, I was just checking the history, CSE is at least 70 years old if you count from the days we were set up as a department within electrical engineering. It was set up in the year 1955 and functioned as a department for many, many decades before we became a school on January 1st, 1991. I actually joined the School of Electrical Engineering, the Department of Computer Science and Engineering, so it gives you an idea of my vintage. And more than that, I was privileged to actually know John personally for a few years. He was actually on sabbatical, I think, the first few months that I was here, but then he later on, but everybody used to speak about John Lyons all the time. I met him maybe 6 months later. We never worked in the same areas. I knew him more as a colleague, a very respected colleague who gave me guidance on what to do in a new school, and it was a department before that. And for example, I learned how to write reference letters for my students from John. He actually gave me a sample of one of his letters when, for the first time, a student of mine asked me for a letter, reference letter. So he was always willing and available in the tea room to have a little bit of a chat and get some advice of this kind. And the school itself, the current state of the school itself, I think it's reasonable to say a few things about it. This year, just now, this term, we have reached 7,500 EFTSLs. So I see former head of school shaking his head. We are around 75 academic staff in strength. We've hired a whole new lot of them. This time next year, hopefully, we should be around 85, right, which is great news. We have 280 PhD students currently, which again is a huge increase on just the last couple of years. And with all the new staff members coming in, we have scope, more and more scope, to build on the HDR student numbers. Apart from everything else, primarily we pride ourselves on the excellent education we provide to the undergraduate and the coursework master's students. Somebody the other day who came from UNSW Canberra called us the bread and butter of the university. Yeah, sure, I'm pleased and proud to be called the bread and butter of the university because we do provide very basic, fundamental education to all the young and old souls who pass through our doors, provide them a fantastic education. Just when I entered the doors, I met a student, ex-student, who apparently knew me 25 years ago. He came up and spoke to me, and we had a bit of a chat. So that's the pleasure that we academics always get in meeting our alumni. He says he's got a startup. He's interested in participating in the life of the school, which is fantastic to hear. So we do want all our graduates, all our alumni, to remember us with fondness, gratitude, that we actually gave them a good education, not for anything else, but we actually gave them a fantastic education, the value of which they would know only when they actually get out into the workforce and work for a few years, and they see what the field is like, what their contemporaries are like, the education that others have got at other institutions, and all the good reasons why we did such a great job. So thank you all. Thank you very much. It's fantastic to see so many of our alumni, colleagues from UNSW and the school, as well as distinguished guests. We have the dean here and plenty of other distinguished visitors. Thank you so very much. And I'm now going to ask for the story of John Lyons video to be played. I believe that's ready. And I will step off the stage and allow you to watch it. Thank you.
Well, I was doing a PhD here in the department between 71 and 75, and John turned up, I think, in 1972, fresh from Bell Labs.
I first met John in 1975 in the third floor tea room of the School of Electrical Engineering. In those days, the Department of Computer Science run by Murray Allen was a very small group of people.
And immediately we struck up a bit of a friendship. The department actually at that time was known as the Department for Electronic Computation. It's a delightful team.
He did a fantastic job of sort of inspiring all the younger students to go and try things.
He influenced the school and most universities around the world in a major way because he brought with him from Bell Labs a novel operating system. And long story short, all of the computers in the university within a year or two were running UNIX, and every university around the world, almost without exception, was using UNIX distributions from the University of New South Wales. Very proud of that.
John had a massive impact in my life. Because of UNIX, I've been able to have a business, a family, and do the things in the world that I wanted to do because I was able to leverage the information that he taught me and build businesses on that information. John was a great influencer, and hey, I'm nearly 70 and I'm still running businesses based on the information I learned from John.
So, and with that we get to the main event here, which is the annual Distinguished Lecture in the honor of John Lyons. We are particularly grateful and pleased to have this year's special speaker, Professor Frans Kaashoek from MIT. And the talk today is particularly fitting of the memory of John Lyons because he's talking about how this work John did has influenced what they're doing now in operating systems teaching at MIT. For those who are interested in a more technical talk on his current research, there's a seminar tomorrow at 11 o'clock in the CSE seminar room. So if you're interested, show up, please. So Frans is no doubt one of the top names, and when I say one of, that's less than a handful, top names in operating systems in the world and has been for a long time. So he's the Charles Piper Professor at MIT CSAIL, so the Computer Science and AI Lab, where he leads the PDOS group, what's the P again? Parallels, yeah, of course, parallel and distributed OS groups. He started off as and this is again an interesting parallel, as a PhD student of Andy Tannenbaum. And of course, Andy Tannenbaum is a trade name in operating system teaching. He wrote probably the most popular textbook, and the UNIX operating system, which is designed for teaching operating systems. He hasn't produced a lot of PhDs, but all of them are well-known people, and Frans was one of them. So he joined then, after his PhD, MIT in '93, was involved in a few startups, did really seminal work in operating system and distributed systems, the massively cited short paper, the Click paper, Click the modular router, exokernel, who is sort of an alternative view of microkernels. More recently, crash whore logic for reasoning about safety of file systems. And one of that has just been mentioned at the SIGOPS strategy workshop last year as a standout in terms of doing real science in computer science, the scalable commutativity rule. By the way, at that event, he picked up his third SIGOPS, the Special Interest Group of Operating System Hall of Fame award. This tells you where he's situated in the world. He's a fellow of the ACM, of the National Academy of Engineering and the American Academy of Arts and Sciences. In his young years, he won the SIGOPS Mark Weiser Award, which is for the SIGOPS Prize for the most promising early career researchers. In the meantime, at least one of his PhDs has won it as well. And he's one of the ACM Prize of Computing. So he clearly is definitely one of the top shots. And I'm so excited to hear what he's got to say about teaching operating systems at MIT and how it relates to John Lyons. Please welcome Frans Kaashoek.
Good afternoon. I almost don't know what to say after so much praise. Can everybody hear me? Good. So it's an honor to be here. And it's a bit of a strange talk for me. I'm not really going to say anything new. It's not a research talk. I'm also not trying to convince you should teach operating systems the way I teach operating systems. I just want to tell you about why we recreated Lyons' commentary in version 6 UNIX, to teach operating systems at MIT, and with the main goal, basically, to pay tribute to John Lyons. And so that's why I'm here. So this joint work with Ross Cox and Robert Morris, a colleague of mine, we always teach together. Just to set the context, for the video already mentioned, the Lyons commentary is a famous book in operating systems. And in fact, I have my 2 copies with me. So it actually turns out to be 2 books. One is the commentary written by John Lyons. The other one is the UNIX operating system source code. That's the version 6 UNIX, the red version of the book, written by Dennis Ritchie and Ken Thompson, and brilliantly typeset by John Lyons to complement the commentary. It was intended for computer science courses here at UNSW. One important thing to note that I'll come back to, notice that the course number starts with 6. In 1997, AT&T changed the license on version 6 Unix, and basically it meant that it was forbidden to teach or use it as a teaching operating system. The book went underground, and lots of people would come together, study the code, read the commentary, and had a good time reading it. And that went on for decades. And I think most people in operating systems, certainly either older than me or younger than me, learned a lot about operating systems from those textbooks. And in fact, I do. These are my personal copies, and is how I learned about operating systems. In fact, I'm told that a lot of people at AT&T, Bell Labs, learned about operating systems from John Lyons' book, which is sort of amusing. So the book went underground, huge impact, and in 1996, actually, it was published again as an official book. And I'll talk a little bit more about that in a while, too. And one reason I think why the book was so extremely successful and influential is that it encouraged students to look at a real system and under the hood and really understand actually how things work. At least that's also the way it appealed to me. So to give you a little bit of flavor, of the book, the insight, here's a page on the left. And one thing to notice is the brilliant typesetting. Namely, there are 50 lines per column, so that means 100 lines per page. So if you have a line number, you can very quickly find the page number, and this is very important. The other thing I highlighted 4 lines of code here. I'm sure the first gen the online students will recognize this immediately. This turns out to be a very important 4 lines of code, and I will talk a lot more about those 4 lines as we go along. Then on the commentary side, this is how the commentary looks. And so it's a typical thing. You notice on the previous slides, we're talking with line 2075, and the commentary has then a paragraph describing, what's going on in this block of code. And as you can see, it starts off saying a small critical section begins here, and I'll talk a lot about critical sections as we go. So that gives you a little bit of a flavor. This is a real operating system that people are running on their computers and time shared by many. And you can just look at the code and actually understand what happened. And this is not an accident. Actually, I was surprised again. Of course, I read the book again, preparing for this lecture. And clearly, John Lyons had a teaching philosophy. And in fact, he started off this is the introduction that basically explains the different teaching philosophies that you can have for operating systems. And he rejects a few, and does that in a very eloquent style. I'll read a little bit about it. The second approach is the building block approach, wherein the students are enabled to synthesize a small-scale or toy operating system for themselves. While undoubtedly this can be a valuable exercise if properly organized, it cannot but fail to encompass the complexity and sophistication of a real operating system. And so this approach was rejected. And instead, the approach is the case study approach of looking at a real-world operating system and understanding how it works. And this approach is basically the same approach that we've been following. And basically, our goal has been sort of extend this case study approach to an approach where you learn by doing. It's now possible, for students just to modify the operating system, the internals of the operating system, and run it, because hardware is so much more powerful than 50 years ago that you can in fact run the operating system virtually on top of your existing laptop, right? And modify the kernel, make changes, which was unthinkable 50 years ago, where a single computer was used, time shared by many students, and probably not hardly powerful enough to emulate a new computer on top of it in software. And so here. Here's a little bit of a fragment of actually booting XV6, which is the copy, basically of version 6 and John Lyons' commentary. So to give you a little bit of a feel for it, let me actually boot it and run it. So this is typically what students will do. They'll run, typing in front of 200 people is always difficult. And boom, we're booting an operating system in a microsecond or something, and you can start playing around. In fact, here on the right, I got a buffer, and I can modify the operating system. This is the file in the kernel that actually all the system calls go through, the key concept in operating system. So, for example, and I do this in lecture all the time, I can just go change it, and for example, print all the system call numbers. And here you go. Even when the operating system starts up, there's 20 system calls that are actually being made. And this is an important point, sort of to realize how important the role of system calls are in an operating system, and also to point out that the system call is just a number, and nothing else. And you can't call a system call with the code corresponding to a system call directly from user space. So it gives you a little bit of a sense, the cool things you can do. So to make it clear, even though I'm running this on my laptop, it actually emulates, QEMU emulates for us a piece of hardware. And in fact, the particular piece of hardware that it emulates is a RISC-V board. And you see in the middle, there's the CPU, and there's a whole bunch of peripherals. Like any computer, there are more peripherals than actually the main CPU. In fact, there's sort of an Ethernet connector. And in fact, one of the assignments that we have is write a simple Ethernet driver. And in fact, the fact that it's real, inspires students to do all kinds of different projects. And so to keep in mind, so that even though it was a demo on top of my laptop, there's actually real hardware under it. Now, of course, this is a lot smaller than the PDP-11, but it's the same idea. So why recreate the Lyons commentary in version 6? The main reason is because we're teaching operating system at MIT, and it just happened to be handy to do so. And our goals changed a little bit over time, and I will talk a little bit more about it, and mostly to address specific issues of the MIT curriculum. So there's no big plan here. And in fact, there was a non-consideration to actually influence any class outside of MIT. It was purely written for MIT students, for MIT classes. And so I'll tell you a little bit about the history, because otherwise it wouldn't make sense why we did it. Before 2002, so this is a while back, the standards computer system class at MIT is General Principles, or it was Computer System General Principles, and it falls in the category of general principles according to Lyon's classification. And so in 2002, I wanted to teach a class that was really learning by doing, like looking at real code and building a real system. And so we started a graduate level operating system, which is not unlike, I think, your advanced operating system class that you have here today. And the students wrote a microkernel, exokernel thing from scratch. Basically, we gave them an empty file, and we gave them the manuals for the x86, and said, go ahead, and by the end of the semester, you better have a running operating system. Of course, we had multiple assignments, but basically they worked towards actually having a running operating system. And that worked really well for a small subset of the students. A number of the other students wanted a little bit more context. And so, in particular, they would like to know how a real operating system actually worked. And so I decided, well, that's no problem. I'll use Lyon's textbook and commentary that was at that point reissued, as you can see here on the right. And I used that for 2 years. And that turned out to be not a success. Not because of the content, but mostly because students were not too interested in learning about the PDP-11 assembly. And so, plus, the C programming language actually changed quite a bit between 50 years ago and now. And so, it was not the same C as they were writing in the lab. So there was a lot of inconsistencies between what they were doing in the labs and actually what was in the lectures. And so that's the point. We decided that maybe what we should do is basically recreate version 6, but in a modern way. We have a modern C programming language for a modern processor, and we did it for the x86, which is why it's called XV6. And that was basically what we did. And that was actually a success. Students really appreciated the fact that they could look at a real operating system and then build their own thing. But they wanted even more support material. So we decided, well, good, we'll write the book. We'll write a book exactly in the same style as John Lyons did. And we started using the book in 2009. Then the department decided it would be good to really have a truly undergrad OS class. And so they encouraged us to build one. And so what we decided to do is, first of all, we ported it to the RISC-V because it was a processor that was used in one of the preceding classes. It was a lot nicer to explain than the x86. And we built labs for XV6 because before it was just a case study, as exactly as in the John Lyons case. But then, since we, I believe in this learning by doing approach, we had to build a whole set of labs for XV6, which we did. And then started using it since 2019, and 2022 it became an official undergrad class at MIT. And so here's a little bit of a flavor. So on the left, is the code, and as you will notice, it's very much written in the same style as version UNIX. The code is about 84 sheets in Lyon's terminology, and the version 6 is 90 sheets. So we're roughly in the same ballpark. In terms of this, took me by surprise. The corresponding book that we wrote was 116 pages. The commentary is 115 pages. So that gives you a little bit of sense. And one reason, my goal actually was to stay under 100 pages. I think it's ridiculous that these operating system books are 1,000 pages. You pay hundreds of dollars, for a book. Nothing mean to say about my advisor, but I think it should be much easier to learn operating system and should be done in 100 pages. So we missed our goal a little bit, but it's pretty close. And then on the right side is really where all the action is, which is where the labs that we ask students to do, and I will talk a lot more about them. And I'll give you a little bit of flavor of what the kind of things we're doing. One of the big surprises has been the adoption of the book and XV6. First of all, at MIT, the enrollment went from 20 plus students to 200 plus students this semester. But more interesting, outside of MIT, I get email from people that actually have reading groups, very similar, I think, as for the Lyons commentary, where people get together and actually read the code and try to understand what's going on. The book has been adopted by many other schools. I don't know exactly how many, but many. The book has been translated to other languages by other people. There are many derivatives, either for research or hobby projects. People have written versions in C++, Rust, Go. There are different hardware platforms. People have it ported to ARM, et cetera, et cetera. And all is done by outside of our, by the community as large. In fact, there are even research papers, based on x86 at, the top conferences in operating systems. So it has been a shock that it actually has been that kind of influential, because there was absolutely no goal. We just wanted to write an operating system, basically replicate it for students at MIT. If you're interested, it's on GitHub, and you can play around with it too. So I think the reason that's so successful, I think it's just a true case of like standing on the shoulders of giants. Version 6 was created by the UNIX room. Many of the people sort of in this, surrounded, version 6 and XV6 actually were very much influenced by the UNIX room. Two of my co-authors, Robert Morris and Ross Cox, basically grew up in the UNIX room. Lyne spent a lot of time in the UNIX room. My advisor, Andy Tannenbaum, spent a lot of time in the UNIX room. And as already mentioned, he was actually very inspired by Lyne's approach. When the book went undercover, he started writing Minix and as an alternative. And in fact, these two copies that I have actually are Andy Tannenbaum's copies, annotated. But I think it just basically speaks to the fact that Lyne's legacy just lives on. And that is a successful way of teaching operating system. So the rest of the talk, I want to do three things. I want to talk a little bit about the teaching goals. Then I want to talk a little bit about parallel programming, because this is one of the big differences between version 6 and XV6. And then I want to summarize a little bit about what the students actually thought, from the class. The talk will be technical, so I apologize. It's John Lyons. We got to look under the hood and actually see how things work. We'll see how it works out. So the teaching goals, that's at least a high level. Basically, we only wanted to educate students to become good at systems programming. Not particularly, very few people are going to build kernels in their life. Some people will, but most people, there's a lot of people that can do systems programming, and it's actually a very important skill to actually get good at. And this class is basically an excuse to train people to become good system programmers. We wanted to explore an operating system that reflects sort of modern practice. And so cover today's core ideas, for example, parallel programming, with a design that students encounter in practice, so UNIX style. And in fact, like many people, when they work in XV6, think it's the same thing that runs on their laptop, except that the thing that runs on their laptop is like 1 million lines of code instead of 10,000. And small enough that students can understand every detail. So basically our goal is at the beginning of the semester, I say, forget the commentary, look at the source code. You should be able to explain the source code to yourself, and then you will do fine in this class. We use a programming language that maps directly to hardware, because I want no mysteries. And so that's C, maybe slightly controversial at this day and age, but it's still widely used in practice, and it lines up also with the classes that precede our class, so it's a convenient thing to do. So why the students might care? Well, I think a lot of students care, and this is sort of nice to know in this day and age of AI, correct, that there's still 200+ students, and in this case, I think here it's 700 students taking the OS class. I think a lot of students want to know, how does a computer work? And why does a program run? Where does my file get stored? All that kind of stuff. And so I think there's one reason, a major reason that people take this class. I think also, if you continue your career and you're becoming a real system programmer, you got to track down bugs and security problems. And the only way to do that is you have to understand what the operating system does. And similarly, if you need to understand the performance of your application, that means you typically also need to understand the performance of your operating system, because most applications don't run in isolation. They run on top of an operating system. They used to send packets over the network, and suddenly things are slow. You got to better understand what actually is happening in the operating system, so you can actually figure out how to make your application run better. And then finally, operating system ideas show up in a lot of other contexts. Whether maybe you implement a database, or in the usual level runtime for some sophisticated programming language, a lot of the similar issues show up. And clearly students do care. The topics covered by XV6 in this book are very traditional. We start out with sort of arguing isolation is important, and the observation is if you're running two applications on your computer, it's better to be the case that they don't trample over each other. And that if one has a bug in it, it doesn't actually cause problems in the second application. So it's very important to have isolation. And from isolation, then we go and do the usual thing. We introduce system calls as a way of a boundary between the operating system and the application. We'll talk about virtual memory, using page tables, and then kernel user transition, because that's the crucial event, where we go from untrusted user code to trusted kernel code. And talk about parallelism and locking, and we'll talk a lot about that, and scheduling, coordination, file systems. In fact, if you look at these topics, it's roughly the same set of topics that actually show up in UNIX version 6 and actually in the commentary. With changes, but the main changes are basically developments in the last 50 years. And one of the big developments in the last 50 years is that you can't get a computer anymore with one CPU in it. And there's a complicated graph that makes that point. On the x-axis in blue, on the x-axis is years, on the y-axis is units. And you can see the blue line is the number of CPUs in a computer. And it basically is 1 until 2003. And then, it starts growing. And the reason is, until then, basically the game was crank up the clock speed and your processor would be faster. But in 2003, basically the CPUs got so hot that you can't do that anymore. But the number of transistors is still increasing, so you got to do something with these extra transistors. So easy thing to do is stamp out multiple CPUs. But this has a profound impact. Because that basically means to get good performance, you have to exploit multiple CPUs at the same time. And so you have to do parallel programming. As most of you know, parallel programming is not easy. And so the talk also will focus on that particular topic. There's a number of other developments since version 6. I think today we're all building virtual memory using paging because it enables a rich a number of opportunities to do cool page table tricks. And so XV6 adopts the paging style of doing virtual memory. It has a crash-safe file system, and so it uses the standard idea of transaction and write-ahead logging to actually implement a file system, so the students know this is the right way to actually implement a file system if you want to have one that actually is consistent, can handle crashes, like your computer crashing in the middle, and you reboot and hopefully your file systems are still there. So that's the current way of doing it, which was basically unknown 50 years ago. On the other hand, it's surprising how many ideas actually have stood the test of time. So for example, standard Unix system calls, open, read, write, fork, exec. Shell is a user level program, I think a big Unix idea. Processes, sleep and wake up coordination, pipes, file system design and implementation, monolithic kernel design. All the topics that in version 6 that basically we all adopt them. It's also interesting to talk a little bit about the things that we don't do. In version 6, actually, XV6 does not implement. We don't do user IDs and access control, not because we don't think it's important. Security clearly is very important, but in fact, it's so important that we have a separate class that teaches security, so we're not doing that here. We don't do swapping for many reasons, but that also means for the people that are very familiar with version 6 and the version 6 commentary, we don't have to explain this comment from Richie, which says you're not supposed to understand this. We don't have a line printer, for obvious reasons, and we don't do job control. So what is it like to teach with XV6? And here's roughly the schedule that we follow. In the lectures, we basically explain the operating system and do demos or live coding, as I did for a microsecond here on the podium. And we use papers to cover topics that we're not able to cover in version 6 Unix itself. So for example, there's for GNU, lecture 4, we talk about microkernels, and we have an L4 paper to sort of illustrate like how you build microkernels. We have a homework, which basically the homeworks are of the form asking a very specific question about the source code. They're typically of the form, in line 2075, this happens. Why? And then, of course, in lecture, we try to answer that question. But the most of the action is in the labs, where students modify the operating systems. And basically, every week, every 2 weeks, there's a lab due. And we'll talk more about those. So the main topic now I want to switch to is this multi-CPU kernel programming or OS programming. And of course, parallel programming in the operating system is not unlike parallel programming in user space. Or if you build a user application, you also have to do parallel programming these days to get performance. And so you use locks to avoid race conditions. You achieve parallelism by splitting up data structures in smaller pieces. But the operating system has a number of unique challenges. And so I'm going to talk about these unique challenges. And for example, the operating system must actually handle interrupts at the same time. And so what we're going to do is we're going to follow the lines approach, and we're going to look under the hood and like how actually x86 manages some of these challenges. And of course, interrupts is nothing new. Yeah, version 6 had interrupts. Here's a PDP 11, for people that still have one. I have one of Robert Morris, one of my colleagues, has one in his office that he got from eBay. But there's a main computer, correct? And the main computer is connected to devices like your disk and your line printer. And when the disk is done, it will generate an interrupt saying, OS, pay attention to me. And it's not uncommon that these interrupt handlers have to modify the same, modify state that also the regular operating system is modifying. And the possible bad outcome is if two concurrent things update the same shared state, is that you can get a race condition. And John Lyons, wrote this up very nicely. This is usually considered to be highly undesirable and to be avoided at all costs. And so let me give an example of a race condition that needs to be avoided. Is a little piece of code, not particularly important. Most important is actually the two lines numbered 1 and 2. So this is we're going to basically push an element on the list, and somewhere inside of V6 this actually happens. It's written in PDP 11 assembly, so I actually wrote it in C to just make it a little bit more accessible. And basically, you allocate a list, and the unfortunate thing can happen is that there is an interrupt coming in between lines 1 and 2. And so the timeline on the right shows that. The operating system executes line 1, basically setting the new elements, next pointer to the list. Then the interrupt comes in. The interrupt, runs the whole push function, so it actually runs 1 and 2. And so basically at the end of it has L prime, and then basically OS executes line 2, which sets the top of the list to the L and not to L prime. And so now we've lost L prime. And so this is one of those highly undesirable, outcomes. The solution in version 6 is to introduce critical sections, as I foreshadowed. And the particular way that actually happens in version 6 Unix is that, and this is probably familiar for the people that actually have done a lot of Unix programming, SPL 6 or later SPL N or X, where basically we turn off interrupts for a little while. In fact, we turn interrupts for like those 2 instructions and re-enable it, SPL 0. And this is like how the V6 dealt with implementing critical sections. In fact, this is exactly, what these 4 lines that I highlighted in the beginning of the talk actually are about. It's actually only the 2 lines that are really important, namely the SPL 6 and the SPL 0 line. And there's a nice discussion here on the right, why this is actually important. But the final paragraph in John Lyons' text is actually very important here, which just says, in passing, it may be noted that the strategy adopted by Unix works only for a single processor and would be totally inappropriate in a multiprocessor system. And of course, John realized that this is an issue. So today, everything is multiprocessor. So we have multiple CPUs, maybe sharing a single memory. Maybe there's some caches involved, but I will ignore those. And the goal, correct, is to get parallelism in the operating system, meaning we want to execute system calls, different system calls like read and write, fork and exec, on multiple CPUs at the same time, so that we get good performance. Which means that 2 CPUs might modify the same operating system data structure exactly as before, correct? And in fact, we have another possible race condition using the same code, but it shows up in a different way. And so again, we have our lines 1 and 2, and if you look at the memory system, correct, the list must reside in memory. And so there's 2 CPUs updating the memory. And so their updates get ordered in some way. And if you get an unlucky ordering, as depicted on the slide, then basically exactly the same thing happens where the last assignment on line 2 actually points to L instead of L prime. And we're losing an element in the list. So highly undesirable. But the key point here is that turning our interrupts doesn't matter. Right? I mean, it just does not solve the problem because we have 2 CPUs running in parallel and they're just writing to memory. So you need a different solution. And all of you, how many of you took the undergrad OS class here? Or the events? Okay, many. So I'm not going to say anything new here, really. The solution is to use locks. And XV6, of course, uses locks. And basically, you insert things of the form acquire and release, where 2 CPUs run, to get to acquire the lock. Only one succeeds. That's the spec of acquire. does the 2 instructions and then releases the lock so that the next CPU actually can get into the critical section. That's why they're called critical sections. In x86, as in many other places, we use fine-grained locking, but it really means that there's many, many locks in the system, and they all have a unique name like KMM lock. And the reason is to get parallelisms, like maybe one system call doesn't really need any memory, but it uses processes, and so it needs the proc lock, but not the memory lock, and so we can run them in parallel. And this is a standard game if you want to do parallel programming. Okay, so now I want to look. The real interesting part is looking under the hood, and we want to understand, like, how do you actually implement acquire? Something needs to happen. So, in fact, there are a number of challenges actually implementing acquire and release, and they're all sort of very operating system specific. It's the case that locks and interrupts interact with each other, locking and yielding the CPU interacts with each other, locks and switching processes interact with each other, locks across I/O operations are a challenge. And so I'm going to go through them one by one. And one reason to do so is because actually we spent quite a bit of time thinking about like what's the best solution that we can explain to students. And so each one of them hopefully has some teachable solution or a teachable thing that you might get out of this. And of course, because the devil is in the details, we really have to look at the details in a very John Lyons style. So x86 uses spinning locks, and here's sort of a fragment of the code. It's incomplete. I mean, this is code that does not work. And it uses the standard idea of using a test and set instruction. There's an atomic instruction that basically any modern multi-CPU processor has, where you can, in one single instruction, you can test and set a particular variable. And so, for example, in this acquire, we're test and setting the locked variable. And if the lock was not taken, it will return 0. Or return 1, and if it was taken, it will return 0, and you will spin around forever, waiting until somebody calls release, and then at the release, the first one that actually executes the test and set instruction will win. So that seems pretty good. So let's just see what's wrong. The interrupt handlers, and we're back to interrupts, they're going to run in parallel with the operating system, right? And so the operating system may be running a CPU 1, the interrupt handler actually might interrupt CPU 2. And run the CPU 2. So clearly, we need locks for the interrupt handler too, because the interrupt handler and the operating system share data. For example, in this particular fragment of code, there's a txBusy variable that's actually being shared. So we need to use locks, and indeed, the interrupt handlers acquire the tx lock and then release it, the tx lock after they update the txBusy. But there's a risk of deadlock now. Because maybe actually the interrupt does not come in on CPU 2, but it comes in on CPU 1, correct? And now we can get unlucky. CPU 1, the OS acquires the lock, and before it releases us, the interrupt comes in. And the interrupt wants to acquire the same lock, and it can't because the operating system is holding the lock. The interrupt handler can never release the lock, and because the interrupts are disabled. And so basically we have a deadlock, and so the whole machine comes to a grinding halt, and nothing happens afterwards. So they're clearly undesirable. There's another example of an undesirable outcome when you start doing parallel programming. So the solution is actually not that different from version 6 UNIX. We just got to turn off interrupts in a critical section. And so any operating system that implements this, basically one of the first things to do is actually turn off interrupts at the acquire, and then turn on interrupts again in the release. Now, you have to be a little bit careful with this because you may have nested acquires and releases, so you need to keep track like where in the nesting you are, but that is sort of the basic plan, right? And the key point here, I think there's a deep point here, namely that a kernel lock must handle 2 types of concurrency. There are basically 2 different types of concurrency. One is interrupt concurrency, or I/O concurrency, if you may want to call it, and the other one is CPU concurrency. And they're just different, and they require different techniques to be solved. So move on to the second one. So of course, the way I've implemented so far, things are not so great because we're never yielding the CPU. We're just spinning there and wasting CPU cycles, and clearly you would like to be better. And so like if you implement like pipe read, like one of the UNIX system calls in a sort of a naive way, you would acquire the pipe lock, look in the pipe. If there's nothing there, you release it, and you go spin around and look at it again, hoping at some point in time somebody actually will stick something into the pipe. But it might be a long time. And so it seems like we should not do this. We should actually give up the CPU. And so the easy way to do it is maybe introduce sleep and wake up. Like same sleep and wake up functions that we saw very early in the talk And in fact, x86 does have a sleep and wake up. So the naive and still incorrect solution is to basically, after we release the pipe lock, we don't have the pipe lock anymore, so totally safe to go to sleep. We go to sleep, and then at some point the pipe writer will do the wake up and wake up the reader. Unfortunately, this is completely incorrect. The reason is there's the lost wake-up problem. It's a famous problem in operating systems. And basically what can happen, just after releasing, the reader releases the pipe lock, the writer comes in and says like, you should wake up. But of course the reader's not sleeping yet, and so the wake-up gets lost. And so the reader actually will never get woken up. Slightly undesirable. So it's another thing we want to avoid. And clearly, we need to have some form of sort of atomicity here, or a critical section, if you will, where we release the lock at the same time that we actually go to sleep. And so this is the typical way of doing this, and this requires a change to the API of sleep. And there's multiple ways of solving this problem, but one reasonable standard way of solving this is actually for the pipe reader to pass to sleep the pipe lock. And so the pipe reader doesn't release the lock. It is actually the scheduling system that first grabs the scheduling lock, and after it has got the scheduling lock, it releases the pipe lock. And this basically stops the lost wake-up problem, because the writer will also grab the scheduling lock, and one of them will go first. And so always you will never lose the wake-up. And the important lesson here is that and this is sort of a bad story for modularity, because basically this means that two separate systems need to know about what they're going to be dependent on each other. Certainly the scheduler is dependent on the caller to actually pass in the right lock. And generally we don't like this, correct? If you want a very modular software, you don't want to do this. But locks basically, if you're not very careful, basically introduce all kinds of dependencies and break modularity. And that's just the way it is. So 2 more, hopefully they'll go reasonably quick. So another problem is, is basically scheduling. The one thread, one CPU may give up the CPU because, for example, it ran for its full time slice, like 4 milliseconds or 10 milliseconds. Some other it should give the chance to another CPU, another process to run. But maybe no other process is runnable. And so another scheduler and another CPU will select this process that actually is suspending itself, and we'll try to run it. And so there are basically 2 operations going on concurrently, namely yielding and actually starting it again. And so, a naive way you might implement this is, you acquire the P lock, you set your state to runnable, you release the lock because you're done with the process, and then you switch to the scheduler. Of course, the scheduler now sees that, hey, there's a runnable process. Let me switch to it. And so we have 2 switches going in opposite direction. And the first switch might not have been completed yet. So the switch actually saves all the registers so that you can resume it correctly. And so what might happen is that we sort of halfway switch, we save some registers, but not all of them. The scheduler actually switches back to that process, and it's going to be totally havoc, right? Because stack pointer might be in the wrong place, the program counter might be in the wrong place, and it's just not going to work. So you're thinking, I know all about locking now. Well, when we need to have a critical section that's slightly bigger than this one, we just need to stick the switch inside of the critical section because, then they're going to be atomic, correct? Everybody agrees that is a good plan. It's wrong. You can see very easily, let's do it. So we do an acquire, we set the P state to runnable, we do the switch, and then we release the lock. But at the point that we switch, do we execute the next line? Not, because we're switching to the scheduler to run something else, right? So the next line actually is never executed. And it was the whole point, we're trying to give away the CPU to somebody else. And so this is not working. And so this actually problem is a real problem. And the solution is actually a very unusual locking pattern. The way actually you implement this is you have to make the P state assignment and the context switch atomic. And so that means that the scheduler has to release the lock that actually the process acquired. And this is a standard way of solving it, but it's a very unusual thing where a different CPU releases a lock that another CPU actually acquired. And this is one of the few places I know where basically there's no way around it. And so this is another interesting teachable point where typically locks are acquired and released by the same CPU, but in a few cases you have to have a different solution. Okay, now the final one, holding a lock across I/O operation. So this is again, for the people that know version 6 Unix by heart, be write is a function to write to the disk, and you pass in the buffer that you want to write. And of course, you need to hold a lock on it because somebody else may want to actually, grab somebody, the other part in the operating system may want to grab the buffer and actually do something to it. But you can't have that because you're writing it out to disk and you can't have anybody else modifying it. So the obvious solution is to grab a lock, before doing be write. But as we remember, spin locks turn off, our locks turn off interrupts. So we're writing to the disk, we have interrupts turned off. We'll never know that the disk write actually finished, right? And so, we've got to do something different. In fact, this requires basically a different type of lock. And the typical way, people in operating systems solve this is like you introduce something what's called a sleep lock, which is implemented in part of spin locks. And here on the right is actually an implementation of the sleep lock. And basically it sets a lock bit atomically, and that is held. And then the spin locks, and that is the one bit that actually is held across the I/O operation, but the I/O operation then runs with interrupts enabled. And for the people that remember version 6 by heart, this corresponds to the be busy flag in the buffer code. So another important point here is that the spin locks is not sufficient to build. There are different types of locks that have different types of semantics, and they're useful in different cases. And here we see 2 different types of locks. In practice, people use more different kinds of locks. So, but to give you a little bit of a sense, what it is, how much fun it actually was to build XV6 and actually implement this. And in fact, supporting parallelism basically touched every part of XV6. And so this is the major difference between version 6 and XV6 is like everywhere there's changes. There are many locks. There are 12 global locks. There's one per process, one per inode, one per pipe. And the lock chains are quite long. Even for like a dirt simple operating system, there are lock chains of 5, the directory inode needs to lock the file inode, you need to write the disk buffer, you need to lock the disk driver, and then lock the calling process. And of course, so there's lock ordering, you got to make sure there's no deadlock, and all the good stuff. So what I'm going to do next, sort of talk a little bit more about what is the student's experience. So this was my experience, and it was great. And so I want to talk a little bit about what the students think about this. So first I will tell you a little bit about what they have to do. So the labs are here on the left in sort of what they're trying to teach. And so the first lab is basically building a couple of Unix utilities, like find and xargs, so to understand the Unix system call interface. Then the next lab is exploring the user kernel boundary. And in fact, what we do, we actually introduce a bug in XV6, and the assignment is basically to steal the data from some other process by exploiting that bug. And so this should not be possible. You should not be able to read some other process's memory, but we make a little error, very typical in an operating system, that actually allow you to exploit that bug to actually break security or break isolation. And this is an example of the kind of bugs that happen all the time and regularly in today's operating systems. Then we talk about page tables quite a bit. So we introduce the notion of super pages to really force students to exploit program with page tables. We implement copy and write fork, and the students do that. Version 6 Unix didn't have that, but it's important in optimization in many modern operating systems. We implement a network driver, a multi-core memory allocator, so a memory allocator that performs well while running on multiple CPUs. And then finally, some file systems, and then the memory map files. Memory map files basically brings everything together, page tables, file systems, everything. Each lab is 1-2 weeks. And this just give you a flavor of the labs, so the way we write them. Here's an example of the copy and write fork. We tend to write one paragraph that explains the problem, and then maybe 1 or 2 paragraphs that suggest a solution approach, and nothing else. And then we basically say, please, go ahead and figure out the rest. And we give a lot of test cases to double check that actually your solution is correct. But the real goal is to make it as short as possible. We don't like long handouts, and we want students to get to coding as quick as possible. Copy and write actually is one of the harder labs, and it requires changes, not many code lines to change it, but they're sort of tricky, and they're like real puzzles. It's like 35 lines to, basically the game is you're going to take the parent's page table, you copy it to the child, you mark the shared pages read-only so that nobody can modify them. If the parent or child modifies them, you take a page fault, and in the page fault handler, you make a copy for the page. And you're hoping that generally this is never necessary, and in many Unix scenarios not necessary because the fork is often followed by an exec, which replaces the address space anyway. And so there's a little bit of code in the page fault handler, 50 lines of code. There's a little bit of code actually in the system call interface because you got to copy memory from user space to kernel space, and that might write over one of those read-only pages, so there's always a little bit of trickiness there. And then the trickiness, you have to keep reference counts on the shared pages because you now have to decide when actually is a page free. And it could be still being used by the child, could still be used in the parent. And again, but the total lines of code is a couple, well, this is my solution, is a couple hundred lines, 120 lines of code. But it is, the kind of bugs you get if you get this wrong are totally spectacular, right? Because, your page tables maybe contain pages that are freed, or actually are the page tables from some other process like that, you forgot to free or you freed too early because you didn't keep reference counts. And so the students come with bewildering to office hours to figure out what went wrong. And the TAs, have a hard time sometimes, trying to figure out actually what's going on. And so this is reflected, I think, in the number of hours that people spend on this lab. The median is 1110, which we calculate 12 hours for the lab. It's 2 weeks, 2 times 6. But you also see that the standard deviation is pretty big. And in fact, there are students that take 24 hours to actually do this lab. But they're very excited about it when it actually gets running. So some of the student feedback, the labs are great. It's a ton of fun. Some labs are very hard and take a lot of time. But in general, the positive is super, super positive. We always ask on the midterm and the final, which labs did you like, which labs you didn't like. And of course, the networking one had some issues. Was not particularly rated as very helpful. And so, this year we spent a lot of time trying to figure out how to make the network lab better so that hopefully, we get more positive feedback. In fact, the midterm is on Wednesday. And so hopefully we'll learn how it's going to fly out. So just to reflect and sort of wrap up this talk. First of all, it has been a ton of fun, for Robert and Ross and me to actually recreate version 6 Unix in the Lions book. Able to use sort of new operating systems ideas and rewrite the pieces that need to be rewritten, but mostly in the same style, and particularly in the same coding style that the version Unix had. We adopted that. This teaching style is rewarding. You can talk, as you can see in this talk, I get excited about locks and talking about the interesting intellectual puzzles that they generate, and the students appreciate that too. And it's also cool, correct? The students, if they have any questions, they can just modify XV6 and run it and explore it, and many do. And so there's quite a bit of interaction. It's great. The adoption has been completely surprising to me. I had no idea that would be the outcome. And I think really the fact that the adoption is so wide that speaks to Lions' approach to teaching operating systems. And so with that, I acknowledge the Unix room, John Lyons, and my colleagues. Thank you. I'm not sure this is actually John Lyons, but the internet says this is John Lyons. So I'm relying on you, Liz, to confirm that this is the correct. I never met John Lyons in person, so this is the Wikipedia page.
So let's move over to the Q&A session. Have we got the Slido link up? Yep. First, thank you very much for your talk, which was very stimulating, and it's actually quite amazing how well these ideas have aged. I'm impressed. I would have never thought that, taking this approach these days. So as I said earlier, I'm happy to take questions from the audience. Raise your hand if you have one, and otherwise submit them via Slido. Alan has a question, please.
Thanks very much for an amazing talk and an amazing piece of teaching. I wanted to dig in. You showed us a long sequence of this doesn't work and it's buggy, and then this doesn't work and it's buggy. How do you fit that together with a here's the code which hopefully has done it right. How do you mix case study of correct with learning by understanding bugs?
I think one reason I like to show what goes wrong is to get a deep understanding of what the source is of the wrongness. And I think once you understand the source of the wrongness, it's also easy to explain why something else is correct. And so I think students understand that way. I guess it's a style of teaching that I think works well. You could try to do it from first principles. For some students that works really well too. My experience is that students understand better first by showing something that's wrong, and then, or what we really do correct is we show the correct version, then we make it wrong, and then we explain, so here is why this version is written that way.
So, quick one before we go to the Slido questions. How big is the class which you're teaching there?
I think it's 200 plus this semester, 207. 200? Yeah.
That's pretty, wow. Okay, so this partially answers one of the questions for which Frans actually doesn't have the full information anyway. How does the MIT course compare to the UNSW flagship course COMP 9242? That's the advanced operating system. It's an unfair question, but I guess one answer is already that they actually, it's a larger size, definitely a factor of 4 or so bigger, but also yours is the introductory OS course, right? So whereas our advanced OS builds on the existing OS course. So this is definitely the teaching to MIT students. While ours are really good, the average quality of, I guess the bottom quality of the MIT students would definitely be way higher than ours. So one of the things you are really torturing your students with is fork. And of course, there's lots of comments made over the years of that fork was a good, appropriate thing for the PDP-11, but it really shouldn't be there in modern operating systems.
Yeah, I certainly resonate with that comment. Like fork and parallelism don't really go together that well. And there's actually a point that we make. So again, one of the things you can do, correct, is like we can talk about the design of the, one reason to do a case study approach like the way John Lyons is that you can look at specific system calls and you can actually explain like, well, this part of the system call is really good, this part of the system call is not good. And so that's one reason. So we do try to illustrate like what the potential shortcomings are. The other hand, you probably call fork when you're actually writing an application or clone, or some version of it. And so in many today's operating systems, there is a fork system call, and there's maybe also a clone system call that combines fork and exec. One of the cool things to explain is that copy and write paging allows you to actually have them as 2 separate system calls. And if you look at the clone system call, man, it has zillions of arguments and flags, and it's not clear that that's the right way to do it. If you write any threading package, you will have something that's called fork. And so, I agree with the point that, there are some limitations to fork. On the other hand, it's still an important system call.
Okay, at the risk of getting into a holy war here, I'm going to pick the most upvoted question is, what's your favorite code editor?
What's sort of my favorite code editor?
Code editor. I guess this is Emacs versus VI.
Well, I guess I'm right in the middle. I use Emacs with Vim mode. As you may have noticed.
So a more serious one. How would you encourage the next generation of academics to teach modern operating systems? Much of what you have shown will work, but where are the gaps?
Can you repeat that question? I didn't get it completely.
So what's your recommendation on academics' future teaching of operating systems, and where do you think are the gaps and what your approach is?
Okay, there's basically a question I can talk the whole evening about. There's many topics that we can't touch in a class, like an undergrad class, and there's many places where operating systems play an incredibly important role. I was just thinking about the foundation of cloud computing. Under it is an operating system, but it's used in a completely different way than is used on your desktop. And so those operating systems, introduce all kinds of other interesting design problems that clearly we're not covering. And so there's a number of topics that I wish we could cover in a single semester, but we can't. Similarly, like, you think, the operating system on your mobile phone, you're still running Linux or some version of Linux, but, it's quite different and has a whole bunch of designs in it that you would not find on your desktop operating system. And so, like, one of the things I think has surprised me over the many decades is, like, how relevant operating systems stay. And I think that one reason is that the workloads change over time, but you still need something that sits between the application and the hardware that manages the hardware for you. And as a result, the operating systems sort of evolve over time. Sometimes, they're all still called Linux, but Linux changes rapidly, to adopt, or to address, the new workloads.
Okay, so this is looks like a student who is interested in OS but hasn't done the OS course yet. How should someone interested in OS start? How can everyone have access to the XV6 resources? I think it's all available.
Yep. It's all public domain. If you go to that URL or just Google XV6, and you can download it. You can look at the labs are public. All the grading scripts are also public. You can just type in make grade and see if your lab passes the assignment. And a lot of people do. And also people sometimes find bugs, and so they email us and I fix them. So it's great. There's a huge community out there that actually tries it. And it's one of the most rewarding experiences when somebody sends me an email from some corner in the world saying, like, hey, I did this assignment. It's really cool. Thank you.
Any questions, live questions? Yeah, Kev, while the microphone gets there, take another one from Slido. What are some dangers or common pitfalls in operating system development that not enough people know about or regard as much as they should?
I'm not sure I can answer that question. The fact that so many students take the OS class, it makes me hopeful that enough people will know about operating systems. And the fact that students are interested in it is just a great sign, right? Like, you would expect in this day and age of AI that the operating system class would go downhill, but we sort of see the opposite. Students take the AI classes, but also take the operating system class. And I think, again, this comes down to the fact that people just do want to understand how things work under the hood. People are curious.
Yeah, so at the conference we were both last week, there was someone presenting a new teaching operating system, which actually was a really interesting approach, I think. But they complained that, well, students are losing interest in operating systems and we need to do something. We have the opposite problem, and I think that lines up with what you're saying. Okay, Kev, please.
I've had the privilege of teaching the undergrad OS course here for the last 20 years, and I'm also a strong advocate for, let's call it, the freedom to explore and learn via, I'm on the OS 161 bandwagon as opposed to XV6, but one day we might switch here, we'll see. But the side effect of freedom to explore is freedom to get lost. So I'm curious, how do you manage or provide debugging help at MIT, because I find that's the biggest showstopper with a broad range in the cohort.
Yeah, that's a good question. Unfortunately, QEMU has great GDB support, the GNU debugger, and so basically you can run XV6 under QEMU and just set breakpoints at arbitrary places in the code. And so we spend a bit of time teaching students how to use GDB. Be able to, and so that way they can track down their bugs. The other hand, I'm a big believer in printf statements. There's a huge amount of stuff you can just learn by actually putting printf statements. So the general story, in our debugging lecture is first printf, and if you can't figure it out, then set the breakpoint in the right places. And we give them a couple idioms, with GDB that tend to be very helpful with XV6. We also the way we have set up the make files is that the students get the C code, but also the .s files and the .o files, and so it's easy sort of to see, how the C corresponds to the assembly, and they're appropriately line numbered, and so everything sort of lines up, so that if a student needs to go one level deeper, it's pretty easy to do so.
Okay, another highly upvoted question is from someone with skin in the game, I take it. What are your predictions of how verification of the OS internals will play a role in future operating systems?
I don't believe in making predictions because they're generally wrong, and so I won't make a prediction. I will say it's an important topic.
And okay, there is another question.
I'll talk about verification tomorrow, so if you're interested.
One question that rose quickly, like a bubble. That's sort of predictable. In what ways might LLMs and vibe coding influence how MIT students understand and engage with operating system coursework?
Great question. I actually had a slide on it, but I didn't show it. Partly because I don't really have a great answer. So there's a couple, I mean, I'm totally in favor that students use modern tools for modern programming. You know, it'd be crazy to forbid people to not use modern programming tools. On the other hand, we want people to understand it. And so one thing we do, one downside of actually x86 being so popular or used in so many places is there are many solutions to our labs out there. And if anything LLMs are good at, is like absorbing all those solutions and spitting out, like, you know, you do tap complete and you get, like, you know, a whole function out of x86 for your assignment. So there's a challenge on the teaching side, and I think we'll have to figure out as we go in the next couple of years what we're going to do about it. There's a couple of things that we do now. One, change the labs reasonably frequently or modify it in a significant way that, you know, and then try it out on LLM to see if it actually can guess what it actually should be. So that's an important aspect. The other aspect is we do check-off meetings in person with students. So students have to come to and see a TA and explain their solution to the TA, and we basically have a standard set of questions that every TA asks or every student to see if they understand the material. And mostly the point is for the students to check themselves to see if they understand the material well enough, and if they're not doing well at the check-off meeting, they at least know that maybe whatever they're doing is not the right way to learn operating systems. And of course, we have quizzes, and you know, we're not allowed LLMs on the quiz. And so you have to do it in person on a quiz, and that, you know, certainly also encourage students to do the right thing, because in the end, you know, you want to get a good grade. But I think there's a real, you know, fascinating problem there, and I don't really know what the solution is. One of the things that we noticed in the last couple of weeks is we use Piazza as one of those platforms for students to ask questions, which then the staff and the TAs answer. And we noticed there's quite a drop in the number of questions asked on Piazza. But if you sort of look at, like, the questions that people asked last year and you sort of feed them to, you know, JetBTP, they can actually very insightful answers. And so that suggests maybe that there's also a way we could use, you know, these new modern tools to actually teach in a different way, you know, where we have to spend less time maybe answering questions in Piazza, but, like, you know, use that time to, you know, improve teaching in other ways. And, you know, this is completely speculation, but, you know, I think, you know, there's probably opportunities like that will actually will show up. I mean, sometimes I try this out myself too. I'm almost curious, like, what actually JetGPT comes up with. And sometimes it knows more about x86 than I do. And it's like, I'm pretty impressed. And that partly is because, like, other schools are using it and using labs and that, you know, are different from ours, and, you know, I learned from that.
Someone on the other side of the fence, I guess. What advice would you give someone someone who's wanting to write a textbook today, a technical textbook? What advice would you give them?
So I've written 2 textbooks. One, you know, for this class, 6033 with Jerry Schalzer, which is a general principles textbook, and then XV6. And both were done in a very different way. The first one was sort of in a very traditional book style. We went to a publisher and all that kind of stuff. The XV6 book is completely different. It's basically a life document, and we update it at the beginning of the semester. You know, you look at all the comments and feedbacks and pull requests, you know, from people all around the world, and then I go through and change the text. The other big difference is the other book is like hundreds and hundreds of pages of text. XV6 book is, you know, as you said, 116 pages of text. My advice, write short, because students like short text. And I like the live text much better than the sort of this, well, you're going to write a textbook and it's a one-time event, and maybe you have a second edition, a third edition. This is a much more convenient way of doing it.
So what does operating systems research look like?
Also a good question. As we alluded a little bit back into one of the answers, I think it's super exciting times. Because there are so many new application areas where operating systems are important, cloud computing being one of them, mobile phones another area. There's the whole area of verification, where there's a whole area of bug finding in operating systems. Operating systems today are a million lines of code. They have to be correct, generally, and so there's a huge opportunity to trying to figure out like how to get them more bug-free, either from the verification side or from the bug finding side. There's also a level up. The kernel is not the only sort of game in town. So I think another project that actually, so I have two research projects. One is on verification of distributed systems, and the other is like trying to figure out how to build a cloud operating system that is suitable for cloud applications. It's sort of a little bit weird that for cloud applications, or most cloud operating systems basically reproduce Linux or Unix faithfully, like all 300 system calls. But a cloud application doesn't use your local file system, right? It stores it in S3 and somewhere else. It doesn't basically sort of really. I think cloud applications don't really need much from the local operating system. They need a lot from inside the operating systems are running inside of the cloud. And so there's also an interesting question about like how would you design a distributed system or a distributed operating system that really sort of targets cloud-native applications. And a lot of the OS ideas apply, but there are also a lot of differences. And so there's like one thing that we're doing is actually building, we're called Sigma OS, a cloud operating system. Anyway, in general, I think I came to MIT and met one of my colleagues, and the first thing he said was, I think operating systems are a dead field. And it was beginning 90s. And then he was at that point not completely wrong. But like a year later, virtual machines happened. And it turned into a complete explosion of really interesting set of ideas and people trying to figure out how to do server consolidation, which led to cloud computing. And so, one reason I don't make predictions.
It's a popular question, but I think you partially answered it, or at least. To what extent do you cover alternative OS design approaches at MIT, like microkernel-based Smiley?
Yep. I tried to address a little bit in the talk to foreshadow it, because I figured this question would come in like a microkernel operating system. The way we do it is, in addition to sort of x86, we read papers from the literature. We try to pick papers that are like not completely obscure and sort of readable for an undergrad, but just get into the mode. Yeah, there's two reasons to do it. One, I want students to read papers and learn how to read research papers from the area, because later in their life they have to do this too. If you want to stay up to date, you got to read papers. And so we basically force students to read papers. And we use these papers then to explore topics that are important and that actually appeal to students. And so, for example, we read the L4 microkernel paper from a decade ago or 2 decades ago by now. And students are very interested in this question. Should you have a microkernel-based operating system? Should you have a monolithical kernel operating system? Should you have a kernel bypass operating system? And those papers allow us then basically to have a serious discussion about it with some technical data in the paper to actually support either case or like what the issues are. And so. And we do this basically for lots and lots of different topics that I think are very important, but you can't cover in the...
So when you get students to read papers and you discuss them, is that done at the scale of the full class of 200 students or in tutorials?
No, for full class.
All right.
And that's a bit of a challenge, but we've gotten better and better at it. Half of the lecture is basically explaining what the paper's about, and then and often driven by questions from students. And particularly in the beginning, some students are quite at loss. You give them a complicated research paper that's quite technical, although we're trying not to make it too technical. And we have to go through and sort of explain like what the technical part of the paper is. And the point here is like, you're going to read the paper multiple times, right? You read it once before class, and presumably by the time the exam runs around, you're going to reread it again. And we have then discussed it at least once in class. And the other thing we do is I said like we give these homeworks, and either the homework is about a specific line of code in x86, or it is about a particular point in the paper. And then we ask students like to think about that particular point and try to understand so that they have something to bite into if you read a paper, because otherwise maybe it's like 12, 6, 7 sections of text. Where should you focus on? And we try to guide students to say like, well, you should really, this is the question you should be thinking about if you read it. And that seems to help.
So there's a few questions that can be summarized into a single one. Someone who really is keen about operating systems, learn about them, know nothing really, or someone actually want to write one from scratch, how should they start?
So the question is, you want to write one from scratch? How should you go about it? It's actually pretty straightforward. There's excellent, like there's os.org, I think. It's a website that basically there are all kinds of people that are very excited about writing operating systems from scratch. And what they do is they document basically the low-level hardware. And so they basically tell you, this is what you need to do to basically get the hardware far enough that you can start writing your first line of code. Because always in booting, there's a bunch of idiosyncrasy of like whatever hardware platform you're running on. And that's hard to figure out, but like they provide a lot of resources. Another thing that a lot of people do is, or some people do, is like they take basically the first file in x86 entry.s and start from there, and then you can write your own operating system from that point on.
Do you try to incorporate how to do post-mortem analysis, like reading crash dumps?
Yes, partly because students actually are forced to. and this is where GDB comes in big time, because you can set a breakpoint right before you crash, and then you can start investigating what actually the issue is. I mean, it was not a joke when I said like in the beginning of the talk, it's like our goal is to make people good system programmers. And I think this is what people makes good system programmers. They're running in those kind of problems and then try to figure out like, how do I solve that problem? And if you treat it like a puzzle, then it becomes reasonably interesting. And so our goal is always to get students to the point, like not, be depressed, that their thing doesn't work, but, get them excited about like, oh, well, something's wrong. I know I can understand every line of code. I should be able to figure out like what is wrong. And, trying to instill that mentality into students. And I think that's, a year back later, that's probably the most valuable thing they learn, in a class like this, is like become good at system programming.
So we've been chatting for quite a while, and we sort of have to start wrapping up. I've got one more question I want to pick from Slido, and okay, we get Mike, but I'll do the Slido one first. Is teaching operating systems like this the best option because modern operating systems are too complex, or are these historical examples just the best option?
Yeah, indeed, in today's operating system, on millions of lines of code, very hard, to cover it in a single semester, right? And x86 is 10,000 lines, totally possible to cover it in a single semester. We do our best to basically take the core concepts that you will see in Linux or any sort of commercial operating system and teach them. And in the most simple and the most straightforward way. And a lot of the things I talked about today, like spin locks, and you can look at the spin lock implementation in Linux, and you will recognize it. It will be different, with things that are slightly more complicated because there are other goals, there's more performance requirements, but you will recognize it. Similarly, you can look at the page table code, you will recognize it. You'll look at the system call, entry system call, and it looks very, very similar. And partly because SV6 is structured like a monolithic operating system in the way you would see it today. And so you can totally see that the lineage, that Linux and other free BSDs and all the BSDs actually have from the original version 6 Linux, or UNIX. And so, by taking those, the key concepts, hopefully, we hope that, students could go back to Linux and sort of try to figure out what actually happened. Like the file system is another good example. We use write-ahead logging. Modern Unix operating systems do that. And the write-ahead logging is much more complicated and much more sophisticated. And we read a paper on ext3, which is the sort of Linux file system that uses write-ahead logging, to sort of explain, we hold up x86 and say, this is slow but correct, and here's how you do it fast and correct. And it's much more complicated, but hopefully, good enough then that you can go back and look at the source code and actually understand what's going on.
Okay, and Mike has the last question.
An honourable position, thank you. Am I coming through there? Yes. I was surprised that you were surprised about the uptake. I mean, we've seen how Lion's ideas really took off, and you've just explained why it is so important to do things that way. We saw Minix spread so much in the 90s. I love that XV6 gets serious about multiprocessing and is on a risk base. It just is right. I'm sold. Then I realized when we had that student question about I want to be on my own and just learn about operating systems, I realized I might have thought, oh, XV6 is great, and said that, and then said, but it's got all this complicated stuff in it to do with having multiprocessors, because it really makes it much harder. And I might have said, oh, I've got this old book, Minix, and maybe you should start there. And then, so really my question is there a kind of halfway point, and do we need it because of the extra complications that taking the modern world seriously introduces into XV6, or do you think it really is the successor of both the Lion's work and Andy Tannenbaum's work, and here we go?
I would not say it's a successor of my advisor's work. I think in Minix and x86 happily coexist in the same way that microkernels coexist with monolithical systems. So I don't think there's really a difference. That's not really the issue. I don't have a good answer, I think, for your question, and partly because as I said early on, it's all driven about what I want to teach MIT students. And I don't really have a much more grandiose plan than that. And I feel like in this day and age, you have to understand locking, and you have to understand parallel programming in the kernel, and there's no way around it. And it would be a disservice not to teach that. And so that's my take. And of course, you can argue about that.
But you've given us a way to do it. Thank you.
Okay, contrary to what I just said, I take one more final question because I really want to know the answer myself.
Okay.
In your student feedback, one student suggested replacing exam by a project. What are your thoughts on assessing students through a project over exams?
I'm much in favor. And in fact, for years I did it. And some of the projects work out great, but many don't. And there's two answers to that. So I mean, in general, one reason we do all the labs is because I believe in projects and making students build things. And I'm very, we always have challenge exercises and things like that. So the students want to do more, they can go off and do more. And the last lab is also more open-ended. I don't like grading exams, but there's a real value for students to review the material, for an exam. And we give all the old exams, they're public, we allow students to look at them. And just the mere, I think, the act of actually having to go and review the material and get ready for the exam is actually the most important part, I think, of actually doing the exam. And so what we noticed basically is with the projects is that people were doing projects, but they also started ignoring some of the lectures and class material because they were focused on their particular project and just forgot to learn, some important stuff. And unfortunately, exams are just a good forcing function to, make sure that people actually really, learn the complete material. And so I don't actually, if somebody has a solution for this particular problem, I'd be very interested in learning about it. Because I don't really know any other way of forcing students to relearn the material. And as you probably all know from yourself, if you review the same material a couple times, it just sinks in a much deeper level than if you just go through it once. And so sometimes I've thought about for many years to actually give an exam and basically ask students just to show up at the exam and then basically give them all an A, because I think the real part has to be is the preparation and not the actual exam.
Okay, we'll wrap it up here. So there will be drinks and canapes out there, and we'll hang out, and you can ask Frans directly for another, I don't know, half hour or whatever. And then I'd really like to thank you for attending and for asking many good questions. And then just please join me in thanking our awesome speaker once more time.
Thank you.